Biochemistry is a little more difficult than what we've been covering so far because we're going to get into inorganic compounds. Organic compounds are even harder than the inorganic compounds, so you've got that going for you. So our inorganic compounds are going to be substances that do not contain carbon. Water, salts, and acids and bases. And water is going to be, it's going to be important because you're made of 60 to 80% water, and all of the chemical reactions that are going to be occurring inside your cells are occurring in water, and your cells are bathed in water. So water is going to be very important. Salts, we're going to cover salts here in a second. And acids and bases. In anatomy and physiology, acid and base balance is going to be very important. And we're going to cover acid and base balance when we get into the blood chapter and to the renal chapter in second semester. Organic compounds are compounds that contain carbon and hence are covalently bonded. Carbon atoms are always going to participate in covalent bonds. Always going to be covalently bonded. So organic compounds are very stable structures. And the types of organic compounds are going to be carbohydrates, lipids, proteins, and nucleic acids. Our organic compounds are made by cells, and cells are made up of these organic compounds. And you know that your diet consists of carbohydrates and fats and proteins, and you probably don't think much about eating nucleic acids, but since your cells are made of all these things and you eat cells, this is what your diet is made out of. Okay. We're going to go into the inorganic compounds first, and we're going to start with water. And water is so vital to life, and so it's important to know about some of the characteristics of water. And the first characteristic of water has to do with its high heat capacity. These first characteristics of water, the high heat capacity, high heat of vaporization, and its polar solvent properties and reactivity actually have to do with the fact that water participates in hydrogen bonding. And if you'll recall, the reason that water participates in hydrogen bonding is because water is a polar molecule. Water is a polar molecule because it participates in polar covalent bonding. So we've got this polar molecule here, H2O. We've got this covalent bond here. We're not sharing electrons equally. The oxygen molecule is pulling heavily on the electrons more so than the hydrogen, these little hydrogen atoms, and so the electrons are spending more time on this part of the molecule, and it makes this part of the molecule more negative. And so when this end is more negative, and when it's more negative, then it participates in the little hydrogen bond. In the hydrogen bond, these are the little hydrogen bonds here. Little hydrogen bonds, hydrogen bonds, hydrogen bonds. And these hydrogen bonds, when you get so many hydrogen bonds, it makes all of them, each individual hydrogen bond is weak, but collectively, if you get a lot of hydrogen bonds, it makes it very strong. Collectively, they're pretty strong. And so what high heat capacity means is if you have a beaker full of water, it takes a lot of energy to increase the temperature of the water. All temperature is a measure of molecular motion. And so this little water molecule here has its own amount of molecular motion. It will be vibrating and vibrating and vibrating. And if you want to raise the amount of its vibration, you're raising its temperature. Well, it can't vibrate much if it has this hydrogen bond attached to it. So these hydrogen bonds are keeping these molecules from vibrating a lot. So if we want to raise the temperature, we have to add a lot of energy. These bonds make it harder to raise the temperature of water. So water has a very high heat capacity because of all the hydrogen bonding and because of the polar bonds. You know that it takes a lot of energy to make water boil, for instance. Now, when we get to high heat of vaporization means it takes a lot of energy to get water to evaporate. And that goes back to these hydrogen bonds. You have to add a lot of energy to get these hydrogen bonds to break. And once you add enough energy, these little hydrogen bonds will break. And once they do, these water molecules will be vibrating enough to get them to break from the surface of the water and to evaporate out into air. Oh, it's a good thing we have a high heat of vaporization. We don't want to evaporate much. But when we do evaporate, it does help to cool the surface of our skin. So that's a good property that water has for us. Okay, polar solvent properties have to do with the fact that water is an excellent solvent. And it's an excellent solvent because the water molecule is a polar solvent. If we put any ionically bonded substance in here, because it has a negative charge on one end and positive on the other, what it does is this water molecule will form spheres of hydration around the ionic or the polar substance, and it will keep it in solution. I'm going to show you a picture of spheres of hydration on the next slide to show you what that looks like. And I'll show you why water can keep something in solution. These water molecules will literally surround the solvent and keep it held tightly within the solution. Water just dissolves things very well. When it comes to reactivity, water is a very reactive substance because we use it for dehydration synthesis reactions, and we also use it for hydrolysis reactions. When we use it for hydrolysis reactions, we use water molecules to split between reactants, to split them apart. And in dehydration synthesis reactions, we usually remove water molecules to form bonds. So that's how it helps with reactivity. On the cushioning side of things, in your body, water is a great cushion, and the best example that I know of is we use it in cerebrospinal fluid around your brain and around your spinal cord to help cushion your brain. Your brain literally floats in cerebrospinal fluid to help cushion your brain. Okay, that does it for water. Let's go down to salts. Salts are inorganic compounds because they do not contain carbon, and they do all participate in ionic bonds. Remember that. Ionic bonds, no covalent bonding. And what happens when you drop them in water is they dissociate. That means they break apart, and they break into their ions. And that means they're going to break into electrolytes. They'll carry a charge in water. And they have to break into ions other than hydrogen ions and other than hydroxyl ions. That's important. If they liberate hydrogen ions or hydroxyl ions, they're not considered a salt. So this is a great example of salt: sodium chloride, calcium carbonate, or potassium chloride. These are great examples of salt that you'll see. So if we were to drop sodium chloride into water, it would break into the sodium ion and the chloride ion, or the calcium ion or the carbonate ion, potassium ion or the chloride ion. Now when they're going to break apart, they're going to break into a cation and an anion, a cation and an anion, a cation and an anion. Remember, there's always going to be one positive charged ion and one negatively charged ion. The positively charged ion is a cation, and the negatively charged ion is the anion. So I'm going to go to the next slide, and what I'm going to show you is those polar solvent properties, how these water molecules would surround, say, a salt. If we were to put sodium chloride into water, how we would form spheres of hydration around a salt. So these are spheres of hydration. I want you to ignore this ugly stuff over here. This shows you a great picture of a sphere of hydration. I couldn't find the chlorine, a picture of chlorine, but imagine we drop sodium chloride into a beaker, and this is what we would get. We'd get the sodium part over here, separated from the chlorine, and the water molecules, the negative side of the water molecule would come up and it would surround the sodium to separate it from the chlorine that would be over here. And this is a sphere of hydration because the water would separate it from its chloride ion. And this is the sodium cation. Now, this ugliness over here, this is actually the sodium cation being separated from the chlorine anion. This is the best picture that I could actually find, but it's a little fuzzy. So this is the same thing as this. We've got our sphere of hydration around the sodium cation, and now here's the chlorine anion. Notice how the water molecules now, the negative end is facing inward, should be facing inward, because this is the chloride anion and it's got a negative charge. So we've separated our sodium from our chlorine here in the sphere of hydration. If we were to evaporate this water away, the sodium and the chloride could rejoin one another and then be in the bottom of the beaker. Now, if we want to continue with our inorganic compounds, we've got acids and bases. Now, the reason it was important to tell you that salts can't release hydrogen ions and hydroxyl ions is because these guys do. Acids and bases do release hydrogen ions and hydroxyl ions. So that would classify them. I mean, that's why we don't want to mix these guys up. An acid is a substance that releases hydrogen ions into solutions. So memorize this definition. This will help you a great deal for the rest of your anatomy and physiology life. An acid is a substance that releases hydrogen ions into solution. For instance, if we were to drop this substance right here, hydrochloric acid, which is a very strong acid. Know this as an example as a very strong acid, hydrochloric acid, right here. If we were to drop this into water, it would dissociate into hydrogen ions. That's what a hydrogen ion looks like. You draw it like this, hydrogen with a little plus here. And chloride anions. It'd be a chlorine with a little negative. This is another example of an acid. This is carbonic acid. Know this as an example of a weak acid. The difference between a strong acid and a weak acid would be this. A strong acid can beat up a weak acid. No, I'm just kidding. Okay, a strong acid, if you drop it into water, it will dissociate completely. There'll be no more hydrochloric acid at all. It would dissociate completely into hydrogen ions and chloride ions. Whereas if we dumped carbonic acid, which is a weak acid, into water, you'd have hydrogen ions, and then you'd have these things called bicarbonate ions, but then you'd still have some carbonic acid. So this guy wouldn't break down completely. So weak acids don't break down completely, whereas strong acids break down completely if you drop them into water. If you put them into something, they break down completely. So hydrochloric acid is our strong acid. Carbonic acid is our weak acid. This is in your body. This is actually in your body. Hydrochloric acid is in your stomach. Carbonic acid is in your blood. So you're going to need to know both of these. And you're going to need to memorize these formulas because these come up in 15 different chapters. Sorry. So carbonic acid is H2, a big C, a big O, and a 3. I see people with something like this on t-shirts every now and then. I don't know what company that is. So if you can put it on a t-shirt, why don't you go ahead and put that on one of your t-shirts. Okay, bases. A substance that accepts hydrogen ions. This definition, memorize it. A substance that accepts hydrogen ions. So if you put a base into a solution, it's going to accept hydrogen ions. An acid releases hydrogen ions where a base accepts hydrogen ions. An example of a base would be like magnesium hydroxide. You've probably heard of this. This is milk of magnesia. So if you drank milk of magnesia, it would accept hydrogen ions. You have hydrogen ions in your stomach, and so that's why it helps your stomach. So they bind up. So another way to define this is substance that binds hydrogen ions in solution, or you could say it accepts hydrogen ions. Sodium hydroxide is lye. You've probably heard of lye soap. This is what sodium hydroxide is. This is a very strong base. So if you want to know an example of a strong base, this is it right here, sodium hydroxide. This is a great example. Hint, hint, hint. Know this one. The bicarbonate ion. This is in your blood. This is your example of a weak base that you have to know 100% for 15 different chapters in this book. It's the bicarbonate ion. HCO3. And see this little negative sign here? That negative sign is actually important. This is the bicarbonate ion. This is a weak base that is found in your blood. It's the bicarbonate ion. It accepts hydrogen ions in solution. I'll go over why that's important in a minute. And another example of a base, and it's in your body. It's a waste product, but it's ammonia, NH3. Okay, we're going to go over pH, acid-base concentration right now, and pH is a measure of free hydrogen ions in solution. People get confused on pH, and that's just all there is to it. pH is not a lot of fun for a lot of people. Some of you guys are out there, you're real pH nerds, and you're loving every minute of this because you already have it down, and you're rolling your eyes, so good for you. But the more hydrogen ions a solution has, and when I say the more hydrogen ions a solution has, I'm referring to the amount of free hydrogen ions a solution has. That means they're free, they don't have a partner, they're floating around, nobody's attached to them, they're just floating around free in the solution. The more free hydrogen ions a solution has, the more acidic it is. Another way to say that is the lower the pH is. You had chemistry a long time ago, I hope, so you know what I'm talking about. The lower the pH is, the more acidic it is. The fewer hydrogen ions a solution has, the more alkaline, or the more basic it is. In other words, on the pH scale, the higher the number will be. So on a pH scale, the pH scale is running from 0 to 14. The lower you are on the pH scale, the more acidic you are. The higher you are, the more alkaline you are. So down here on this pH scale, we're talking lots of free hydrogen ions. Up here on the pH scale, little to no free hydrogen ions. When we're in the middle of the pH scale at 7, you're neutral. And we're going to get to the next slide where we actually see the pH scale, because we're going to incorporate the hydroxyl ion as well. And down here at the bottom of the screen, I have a neutralization reaction. This doesn't happen in the human body, but it's a neat little reaction. The last screen, I gave you these things. What are these things? What is this? That's right, it's hydrochloric acid. Now what is this? That's right, sodium hydroxide, it's lye. If we were to throw this very strong acid in with a very strong base, it would actually form this. What is this? That's right, it's a salt, it's sodium chloride. It would form salt and water. Crazy, huh? Don't go doing that at home. I don't trust it. But sodium, we mix this up. H plus OH gives you water. And then we have the Na and the Cl. It's a neutralization reaction. This is never going to happen in the human body. Don't go swallowing hydrochloric acid and lye just to figure out if you can make water and salt. That just, yeah, not good. Okay, on to pH scale. Now this is the true pH scale. It's a logarithmic scale. It's on a base of 10. This is the true pH scale. We start down here at 0, and this is giving you examples of things with pH. You know, bleach is actually very basic, and ammonia. Don't mix bleach and ammonia. That'll kill you. Okay, oven cleaner is very basic, and here's sodium hydroxide up here that we were doing lye. Wine, look at wine, how acidic it is. Black coffee, you wonder why these things hurt your stomach. Milk is actually a little acidic up here. Some things in the human body. Your blood is actually slightly alkaline with a pH of between 7.35 and 7.45. That. Egg whites are a little slightly alkaline. That's not in your body unless you eat it. But blood, look at blood. Right there. All right. Hydrochloric acid in your stomach is very acidic. So those are just some common things that they give you the acidity for. But here's her neutral pH is 7. If you go over here, it shows you hydroxyl ions and hydrogen ions. On the pH scale, we're looking at hydrogen ions. pH is 7. Hydrogen ions and hydroxyl ions are equal. But as we go down, we've got lots of hydrogen ions down here at a pH of 0, lots of hydrogen ions, and no hydroxyl ions. This is actually a very small number when we get 10 to the negative 14. Very large number at 10 to the 0. Now when we go up to a pH of 14, we have no hydrogen ions and tons of hydroxyl ions. So these reverse up here. I want you to focus on the hydrogen ions for me, not the hydroxyl ions. What else do I want to tell you about it? I want to tell you about how many hydrogen ions you have as you go up and down this scale. When you start out at any number here, if you're going from a pH of 7 to a pH of 8, you're increasing by a factor of 10. Or let's say if you're going down, if you're going down from 7 to 6, you're increasing the amount of hydrogen ions you have by a factor of 10. Each jump you do, you increase by a factor of 10, by a factor of 10, by a factor of 10. So if we're going from pH of 7 to a pH of 6, we have 10 times more hydrogen ions in a pH of 6 than we did in a pH of 7. But from a pH of 7 to a pH of 5, we have 100 times more hydrogen ions than we did in a pH of 7. Why? Because we do 10 times 10. 10 times 10 more hydrogen ions. If we start out here with a pH of 10, and we want to compare a pH of 10 with a pH of 3, we would say 10 times 10, what was 10 more times 10 times 10. So how many times more? I'm going to write this down because I'll mess it up. I'm bad with math. So if we're going to start out with a pH of 6, and we're going to a pH of 3, and we want to know how many more hydrogen ions that we have. How many more hydrogen ions do we have from a pH of 6 to a pH of 3? What we do is we multiply, and we see that we have 1,000 times more hydrogen ions at this level. We just add zeros, basically. One more set of zeros. From a pH of 6 to 5, we have 10 times more hydrogen ions. From a pH of 6 to 4, we have 100 times more hydrogen ions. From a pH of 6 to 5 to 4 to 3, we have 1,000 times more hydrogen ions. So you just add zeros as you go along. 0 to 0, 0. You're multiplying by 10 for each little factor. Now, as we go up on the scale, you're taking away hydrogen ions. So a pH of 12 compared to a pH of 11 has 10 times fewer hydrogen ions. So we're working on a logarithmic scale. So you're taking away hydrogen ions as you go up, you're adding hydrogen ions as you go down. On buffer systems, because pH is so important in the human body, because we want to maintain our blood between a pH of 7.35 and a pH of 7.45, this is a number that you should know, we rely heavily on these things called buffer systems. And buffer systems resist radical shifts in pH. So we have things like proteins that help maintain our pH, but we also have weak acids and weak bases that work together. And the biggest buffer system that you have in the blood is called the bicarbonate ion carbonic acid buffer system. And this is a buffer system that you should just give in. Go ahead and memorize this and know it. Say it before you go to sleep at night. When you wake up in the morning, say it. Write it on a little piece of paper. I've seen some of you with tattoos. Go ahead and tattoo it on your arm, tattoo it on your leg, tattoo it on your boyfriend's back, whatever you want to do. Tattoo it somewhere and get used to this, because you're going to have to know it. You're going to have to know it this semester. You're going to have to get to know it next semester. It's your friend. So this is carbonic acid. This was your example of a weak acid. So I told you you're going to have to know that. This is your example of a weak base. Told you you're going to have to know that. And this is the hydrogen ion. So this is how and this should be actually an arrow that goes in the opposite direction as well, because this is a reversible reaction. What happens is, in the body we have carbonic acid floating around in the blood, and this carbonic acid can break down into the bicarbonate ion and the hydrogen ion. It can break down to release these things. Now, if your pH in your blood is getting too high, if it's getting up in this range, because this is a high range, if we're going in this direction, we would become alkalotic. Our pH would be too high. We would want to go back in this direction. Our pH, we would want to drive our pH down. And the way we would drive our pH down is we would want more hydrogen ions, right? And we can't drive to Rite Aid and pick up hydrogen ions. We just can't do that. And we have a store of hydrogen ions in our body, and that store is right here in carbonic acid. Acids, by their very nature, what they do is when they're in solution, they give off hydrogen ions. That's the definition of an acid. In solution, they give off hydrogen ions. Well, floating around in your blood, you have carbonic acid. So if we need it, carbonic acid can release hydrogen ions. If for some reason the pH of your blood starts to drift higher in this range right here, carbonic acid can break down to release this bicarbonate ion and hydrogen ions. Well, if you release hydrogen ions, what's going to happen? The more hydrogen ions you have, you go down in pH, right? So if you release this hydrogen ion, your pH is going to go down in this range. So that's what buffer systems do. As this carbonic acid releases the hydrogen ion, your pH goes back down. So buffer systems resist any radical shift in pH. So also floating around in your blood, at all times you have this bicarbonate ion and you have hydrogen ions. What if the opposite were happening? What if your pH started to go down? What if your pH started to drift down past in this range of 7.35? Well, if your pH started to go down, that means you have too many hydrogen ions. Well, if you have too many hydrogen ions, you can't just spit them out. They're in your blood. So what can we do to bind up these hydrogen ions? What in your body binds up hydrogen ions? What substance accepts hydrogen ions in solution? It's a base. What are some examples of bases? Oh, the bicarbonate ion is an example of a base. There's the bicarbonate ion. So if we have too many hydrogen ions, that's going to make our pH low, right? So if our pH is getting too low, because we have too many hydrogen ions, luckily we have this bicarbonate ion floating around, and it can accept those hydrogen ions, so that's what it does. This bicarbonate ion will bind up those hydrogen ions, and it will make carbonic acid. And then our pH will start to go up. So this buffer system is resisting a radical shift in pH. Our pH was going down because we had too many hydrogen ions. The bicarbonate ion bound it up and made carbonic acid. Some of you are thinking, we made an acid and our pH went up. I don't get that. we make an acid. Acids, you know, acids, I don't get it. But you've got to remember that that this hydrogen ions, only free hydrogen ions are the ones that mess with your pH. Only free hydrogen ions. This hydrogen right here is not messing with pH. This acid's not doing anything to mess with your pH. Only free hydrogen ions mess with pH. They're the only ones. So these buffers are going to come back and back at you. So memorize this and understand it. And if you have any questions with it, ask me. Like I said, don't be afraid to tattoo it on a loved one. Okay, that's the end.